We have been discussing the concept of model regularization in the context of polynomial regression, and this is our error function, and we are trying to fit a sine function. Although the preferred solution is this, if you just carry on with your optimization following this function only, your model will go to an unexpected solution. In the machine learning literature, we call it as overfitting. Regularization actually helps us control overfitting. How? Which we have discussed in our last lecture. We also discussed some naming conventions. For example, if your regularizer is a L2 regularizer, we call the regression model Ridge regression. And if you are using L1 regularizer, we call it a Lasso regression. So in this part of the video, I will be demonstrating through a notebook and for a practical application. And the task that we'll be modeling is diabetes score prediction. The notebook link is provided in the description, so I suggest you go through this notebook, run it. It is quite self-explanatory. So we are modeling the diabetes score given features like age, sex, BMI, blood pressure, and few other variables. So let's first load the dataset. And we split into features and labels data frame. And let's look at some of the values in the features data frame. So you can see that the age features, then sex, BMI, blood pressure, and some other features. Now we plot the data for one feature BMI, and we clearly see that there is a linear relationship. Now I just assign those features into X matrix and labels in Y matrix, and then split the data into half training and half testing. And here I instantiate the linear regression model. And we didn't put any parameter here. That means the model is not using any regularizer. And we train our model. And let's look at their training error. We are using the mean squared error, which is 2726. At test time, we have 3075. So we see there is a difference. Okay. Now we do the same with L1 regularizer model we call Lasso. You see that now we have a little bit higher training error but less test error. And don't worry, we will see all the numbers at the end of the notebook. Let's do for the L2 regularizer or Ridge regression. And here you see that the difference is even smaller. Okay. Now we plot the results in bar charts. So you can clearly see that without regularization, the difference between the blue bar and red bar is the highest. So if you hover over these graphs, you can see that 3075 and then 2725, 3058 and 2860, and here 2900, and then the test error is 2984. Okay, so here you can see that the results are quite the same at training time and test time. Okay, so one conclusion we can draw that these two regularizers were able to reduce the difference between training and test error. And how they did that? Because they somehow stopped the model to move to this direction. Okay, they actually balance the performance. One final thing, if I add up the coefficient values for the model without regularizer, the numbers are 3260. Okay, if I add for Lasso or L1 regularizer, what do you expect? It will be way less. Okay, you can see that almost half. Okay, if I sum those absolute values. It will be kind of similar for the L2 regularizer as well. One thing I want you to pay attention. So do you see any difference between Lasso and Riz? Why Lasso is preferable in many cases? Because out of 10 input features, 1, 2, 3, 4, 5, it actually managed to make 5 of the coefficients 0. That means you don't need those input features to do your prediction. It is a technique what we call feature selection. In our coming classes we will be discussing about that, but as we have an example here, we can clearly see that this guy Lasso, or the polynomial model with L1 regularizer, was able to actually drop some of the features. So this is one big advantage of this model. Performance wise they are close to one another, but this is an additional advantage L1 regularizer gives us. If you have any questions, feel free to ask me. Thank you so much.